Hi there. I'm Jacob Nelson. I'm part of the Systems Research Group here at MSR, and I'm delighted to welcome all of you to this mini workshop on Ultra Ethernet today. We're very excited about everything that's happening with Ultra Ethernet and all of the input that Microsoft has had in driving this new standard. And so I'm excited to welcome a number of people to tell us what Microsoft has been doing and how the standard is progressing. Saurabh is the CVP who's responsible for system planning and architecture in Azure hardware. Torsten Hoefler is a professor at ETH Zurich as well as a consultant for Microsoft. I've been a fan of his work for years. And Abdul Kabbani is a principal network hardware architect with a long research career as well. And so with that, I will turn it over to Saurabh to get us started.
Good, thanks. And I do have a mic, so hopefully people can hear me. And so firstly, good morning and good afternoon, good evening if people are joining from across the world. I'm Saurabh, and like I said, I lead the systems planning and architecture for Azure hardware systems, and been doing this for the last 7 to 8 years. So when Torsten and Abdul kind of asked me to come and say a few words, I said, oh, this is really an exciting time, and I'll take any opportunity to talk about this tectonic shift or the platform shift that we are seeing in AI. Satya likes to call it, I think he said it in Build, it's like the middle innings of AI. And being a Formula One fan, I always reflect on what does it mean. And if people watch races, they always say the first lap is quite chaotic. Like it's like there's a lot of drama happening around just the first corner. And then when it gets into the middle stretch, if you ask any principal team lead, he'll always say, I think races are won in the middle innings sometimes. And it's really, they may not be as flashy, but they're more decisive. And here we are in kind of the middle innings of AI, and sitting in the infrastructure side of things does really feel that we are moving from really now delivering consistent, high performance, but also lap after lap, giving the performance, the quality, the availability, the efficiency, and doing innovation at the same time. This is really the middle innings of AI for AI infrastructure. And I think I just want to go through some of these shifts, like what's happening under the hood, maybe in a few minutes before I hand it off to Torsten and Abdul to go into the details of the technical talk. But I think one thing that really stands out is, as Satya has laid out this mission and vision for us to deliver the highest scale infrastructure at the lowest cost, and driven by the workload that you have to fall in love with, which is AI today, right? and so we just announced about 2 gigawatts of data center expansion in the last year alone, and that's more than what we had in Azure just 3 or 4 years ago. So significant expansion going on, $80 billion of capex being spent, and what's happening under the hood is really around 3 or 4 macro trends on infrastructure. One is that we are really being an AI-first data center. Like the data centers that are being built are designed with AI in mind. And if you look at one of our AI data center, that's going to perform 10x the performance of the fastest leading supercomputer. But it's not just AI, it's also the compute and the storage that goes along with it, and the ability to now build a holistic infrastructure that canonical workloads like ChatGPT or even GitHub Copilots and some of these that are scaling can truly lead and deliver the experience. So that's the expansion piece of it. Another expansion, I would say there are 3 layers that we're continuing to focus on. First is on the unit of deployment, which is the silicon and the rack infrastructure. We were the first one to go into the world and the fastest ramp of the GB200 infrastructure, which is now leading the performance and benchmarks of everything that we've run today, and we'll be running ChatGPT on that infrastructure itself. But along with that, we are continuing to focus on diversity, so we continue to deploy AMD and our Maya systems, and that's the first layer of the silicon and the rack infrastructure that we're building. The second shift that's really happening is around the liquid cooling and the sustainability efforts that goes along with building such high massive expansion comes with a lot of responsibility. And so we're seeing a massive shift of megawatts moving through air to liquid over the next few years, and how do we kind of continue to operate that at the highest scale, but at the same time with the best level of efficiency and operational excellence is the second shift. And the third one, which I think if the crowd here is really wanted to talk about, is the networks, right? I mean, we've got clear networks that are beating hard of the infrastructure today. And whether it's within the data center, whether it's outside the data center, we have announced the AI WAN, which is one of the most highest performance scalable AI network connecting multiple data centers together so that the job can not just be run in one data center, but is interconnected across multiple data centers. We have work going on inside the data center itself with both on the front end networks as well as the scale up networks. So I think the network aspect of it is kind of one of the third and the most exciting personally to see some of the advancements going on. So not only are we delivering on the diversity of silicon, we are doing this massive shift towards air to liquid and the operational excellence and rigor that goes with it. And then we are reimagining the networks for this AI workload. Now, UEC, I mean, I've been following the journey for UEC for the past few years personally, and just the need for something like this has been so critical right now, especially when we look at the legacy of the Ethernet and the changing requirements that AI brings in. And the principles that UEC was established on are kind of foundational to this innovation. The principle of delivering high performance that you need, this is the backbone of the network that's going to happen, and the scalability that goes with that performance. But at the same time, you're building on top of a known Ethernet stack that can make it interoperable, that can make it open for all of the companies to innovate on. And then the third piece of it is the economies of scale, right? That's so again, those three design principles of high performance and scalability, the openness and interoperability of Ethernet, and the ability to drive the economies of scale, and the ability to use a lot of the learnings we have on Ethernet to be able to then apply them to this next generation workload. That's what personally is exciting to me. So again, thank you for all of the work that this community has done to publish that first 1.0 spec. I'm sure that itself is a lot of exciting innovation that is going to help us in years to come. And I think there's some great work going on in the roadmap as well as we look forward to how the UEC and the Ethernet ecosystem stacks up for AI. So again, thank you, Torsten and Abdul, for bringing in. Thank you, everybody, for participating in the workshop. And I'm excited to hear how the rest of the day goes. So Torsten, I'm going to hand it off to you.
Thank you. Turn this on. Okay, thank you very much, Saurabh. I'm assuming I'm audible online as well. And so this was a wonderful introduction, just framing the idea and what we are doing and what we are doing at Microsoft, but also what we are doing specifically to Ultra Ethernet. By the way, I'm supposed to remind everybody who is a Microsoft employee or Microsoft NDA'd in the room, this is a public meeting, so this is going to be recorded, this is going to end up on YouTube, so it means whatever question you're asking here, do not include internal information in that question. There will be a private meeting right after this meeting where you can stay in the room or call into the Teams link that you've seen, where we can then discuss confidential issues, okay? But let me start right away with Ultra Ethernet. Thank you so much again. This is a large effort. This is an effort with more than 100 companies involved, actually many people. There is the whole specification. There are two numbers on this paper abstract that I want to emphasize here. So the specification is 562 pages. Most of you will probably not enjoy reading those pages because it's a specification. It is really not written in a way that makes it super interesting. However, it has a lot of really nice features in it. And so the authors of this spec basically have gotten together to extract the really nice features into a much smaller kind of scientifically minded document, which is this document here. So you can see here, these are the key editors of the pieces of the specification at all the different layers, like ID is in the lower layers, and then the whole layers. I don't have enough time to tell everybody. You see that there's a good mix of companies also involved. But why did we actually do this? That may be another interesting question. It's also on this paper. Because there's a 100x multiplier 1000x multiplier that changed from the last time when we specified such an interconnect, which was InfiniBand, nearly 30 years ago, until now. And that 1,000 times multiplier that changed is really the computational efficiency per moved bit. So Moore's law has been moving very, very fast, exponentially, every 18 months, doubling. And networking, unfortunately, the number of bits moved or the bandwidths, they have not been keeping up with this. So the gap between the compute capabilities and the network bandwidth has increased significantly, which is positive. Right? So many people see this as negative because there's a problem if you're a system architect like Zora. You're like, oh my God, how do I now get this bandwidth? I need more and more NICs, right? Which is what we do. But from a network design perspective, it's positive because suddenly you can employ more complex hardware on the NIC itself, more complex logic on the NIC itself, because that's literally coming for free. Right? And that is a big design point in Ultra Ethernet. Because InfiniBand at the time was designed for an extremely weak computation with respect to the network bandwidth. So they had to make all kinds of trade-offs. It was a great design at the time. They had to make all kinds of trade-offs, like go back N and very, very simple in-order delivery and all of that. And now, with 1,000 times more compute per bandwidth, we can relax all of this. We can do full out-of-order delivery, full dynamic adaptive routing. We can do everything on the NIC. We can build a really silly network, a really high-performance network that just switches packets in the switch. Dumb, like many people say, but I call it high performance because it's simple, very simple pipelines, and put a lot of complexity, a lot of computation into the NIC. And this is the philosophy of Ultra Ethernet today. Just as a general opener, I would recommend all of you to look through this paper if you're interested, because that really summarizes all of the talk nicely. It is much longer than the talk, has much more details than the talk. But again, you can also look at the full spec where you find all the details, but they may be really well hidden. So they're all in there, but they may be well hidden. But first, I want to talk a little bit about the workload classes, because we're all here to do real computations. And I want to arrange them along two dimensions. One is the bandwidth sensitivity, which we measure in flops per byte, essentially. So how much computation per byte do we have in that application? So going from low to high. And the second one, I mean, this is an easy one because the bandwidth is just a matter of area and cost. So we can just add more NICs and we get more bandwidth. That's a very, very easy thing to do, well, if you have money. The second one is quite hard. Is the latency sensitivity now, which goes from high to low. Again, in this scale, now we have 4 quadrants that we can talk about. Unfortunately, the latency sensitivity is not, latency is not very easy to beat, right? Because we have the speed of light. There is a lower bound if you have long cables. Inter-data center communication is an especially bad example of this. But the latency sensitivity itself is extremely hard to measure for an application even. Here, for bandwidth sensitivity, we just measure flops per byte. It's easy, you just do it. Latency sensitivity is not so clear, as we'll see in a couple of minutes. And it's extremely hard to improve, as I mentioned, because we have limits with the speed of light. And so when you design a network, you really need to be aware how important latency versus bandwidth is, because there are very often trade-offs you have to make between those two things. And it's very painful. It can be extremely painful. Right now at the IEEE, we're discussing this outside of Ultra Ethernet is basically the base of Ultra Ethernet, where Ethernet is there, concatenated FEC and things like this. Heavier FEC to enable higher bandwidth, which is going to increase the latency. Bad. Is it bad? We don't know. Right? This is why I want to spend a couple of minutes on workload classification to just remind us that there is a trade-off between those two. So now in the low bandwidth sensitivity, high latency sensitivity area, there's not too much actually. That's pretty funny. So some graph computations are there. The graph 500 is kind of in this area. Not our workload that we have to love now, so, which is okay. In the high latency sensitivity and high bandwidth sensitivity, if we go back to the more traditional field of high performance computing, modeling, and simulation, we find a lot of strong scaling workloads there. If we scale to very large clusters, that's the case. We find weather and climate simulations typically there, great, but hey, aren't we here to talk about AI? Exactly. LLM inference is squarely in that quadrant. It's really sensitive to everything, and it's actually getting worse, as we'll see in a couple of minutes. So then, bandwidth sensitivity and low latency sensitivity is weak scaling HPC workloads. So workloads where I have a lot of work per item done, and of course, generative LLM training and AI training. So that doesn't need a lot of latency sensitivity, but it needs a lot of bandwidth. Okay, well, then you wonder what's here, like low bandwidth sensitivity and low, so basically the network doesn't matter quadrant. Yes, independent jobs, large-scale HPC, but that may actually be a major business. So we don't want to ignore those too much, but we are really living on this side here somehow. And what is even getting worse slightly, what is slightly annoying, the LLM inference side is pushing to the top right with growing context lengths, with all these new things like test time compute, And wonderful reinforcement learning I'm doing at runtime, oh, this is just really bad. There's more bandwidth and more latency, lower latency, higher sensitivity in both dimensions, and really badly in many ways. Okay, but now the question is, how do we assess the latency sensitivity of a real application? As I mentioned, that is not so simple. You cannot simply compute the bytes, the flops per byte or bytes per flop that you use, because it is a problem. For example, if I have a large message, kind of by definition, the latency doesn't matter so much. Because if I'm sending a megabyte, I don't care about the microsecond latency because I'm hiding that in just the bandwidth term of the message transmission. Okay, so now it depends on our average message size. Well, that may be in a very simple metric. If we would just have the average message, no problem, I can totally measure that. But no, it's even worse, because I can pipeline and overlap even small messages. So you could say as a first heuristic, small messages are latency sensitive. No. Small messages have the potential to be latency sensitive. If you overlap them with computation and if you schedule them well, they're actually not causing latency sensitivity. And now it gets problematic because you now have to worry about the critical path in your application. Okay, so are these small messages actually, if they're large, we don't care. But if they're small, are they on the critical path? Yes, no. Not so simple, but what you can do is you could look at the execution graph of this application. You could actually look in detail what the application does. We've done this in our research group, so you can take an MPI program or a nickel program, you can trace it as a trace. You can build these execution graphs, and you can then actually use a pretty cool technique that I just want to quickly mention. This talk's not about this technique. I just want to mention that you can do it. You can run a linear solver, and you can determine your latency sensitivity at the end. That was published last year at SC24, was the best paper, achieved the best paper. And what did it actually show? And this is quite interesting, also for the design of next level architectures. So it showed that for HPC applications, and now we have new data for AI applications, but not on that slide yet, that you can grow the network latency, okay? And you can determine when does it slow down, in this case with the red line, by more than 5%. So here in this case, if I'm adding 22 microseconds to my network latency, this particular application, MILC and 128 processes, is going to go 5% slower. If I'm adding more, then it's going, of course, even slower. So you can now look at this as a sensitivity metric, right? So you can look at another application. Oh, that application can take 65, here in this red one, can take 65 microseconds before it slows down more than 5%. Oh, that's great. Another application can actually take 600 microseconds before it slows down, because that overlaps really well. That's a climate application. Oh, nice. But not so nice, because these applications, they look pretty much the same from a bandwidth per byte, from a flops per byte perspective. So now it's not so simple. So we basically find that it varies by nearly 2 orders of magnitude, at least one to 2 orders of magnitude, the latency sensitivity of applications. So we would need to understand how that goes. So now, if you're in an operation like Azure, for example, how do we do this? How do we find out for our applications what we do? Well, we could use that tool chain. We are actually collaborating with people in Azure to use that tool chain. And what we also have, we have, and this is now getting towards Ultra Ethernet, we have a tracer and a simulator that is just published. It's actually going to appear at SC25. It is the best paper candidate, so we'll see if we again manage to get the best paper for this. But the idea here is that we trace nickel and MPI applications, and we have 3 different classes of applications. High-performance computing first AI, of course, HPC comes second. First AI is like DLRM, Llama, Mistral, MOE traces, up to 256 Grace Hoppers. Again, we are working on larger traces together with Azure. We have HPC applications, and we actually have the public Azure Direct Drive protocol. So the version that has been publicly released, there's a YouTube talk on explaining how it works in detail. We have that full protocol implemented in the tracer, and you can literally run read-write traces through this, and it'll translate it to network transactions, because that protocol is not very simple, because it replicates to 3 different nodes and does all of that. So now we have a full tracer, and it goes into the standard goal trace format, which is, by the way, used in Microsoft internally pretty heavily at this point. So there are multiple different orgs using that trace format. And it feeds into the official UEC simulation environment. So now we are coming to UEC. So that's HTSim. So you can now actually take your workload, run it through the tracer, and run it on the official UEC simulator that simulates, that is approved by the committee, so to say. That is the official thing. So that's quite nice. We can do this. But now I want to make one step forward. Going back to Saurav's original statement. At 2022, Satya said we're really building the world's computer. Like this is what the goal he set out for Microsoft. Actually, I've heard this before 2022 even, but 2022 it went public. So keep that in mind. So he charged the whole company to build that machine. And now, well, this is how it looked like a while ago. So we have 60 regions, 300 data centers, great. But then, what happened then? Well, then Saurav came and changed that slightly, because as we all know, we are now going towards the workload we all love. We are not building the world's computer. Actually, we are building the world's AI supercomputer. And where did I steal this slide? From Saurav's OCP talk. So you should watch that talk. The link is down here. And you can see more details on how Microsoft envisions that going forward. So that is really a wonderful visionary way to look into how do we build the future of Azure, or the future of computing in some sense. And now it moved from the important piece from computer to supercomputer. And that is quite a big of a change, because how do we move from a normal computer, an good old data center like we used to run Office and I don't know what, to a machine that can actually enable AI everywhere, AI in Office. AI is all about performance, because these workloads are extremely demanding. So now we need to be performance-centric and performance-critical all through the stack. At every single network drop, we want high performance now. And this gets very interesting. The first observation is that the network itself is really the cardiovascular system, including the heart of any data center. If you think about it, connects the units. If the network doesn't work, we are dead. Azure Networking knows this very well, so they're going for high reliability typically. You have to be extremely reliable, but the new goal is not just to be highly reliable, but also highly performant and deliver reliable performance at the same time, because nobody wants to wait for their query. So that is interesting. We've actually, in an academic context with some industry partners, we've pointed this out earlier, also about 2022, that we really want to converge hyperscale data centers and high-performance computing networks to something that is a single interconnect, right? And now, it is obvious from the market, as Saurav also mentioned, that this has to be Ethernet. There's just no choice. I mean, this is the ecosystem that's there. It's a gigantic ecosystem. We cannot change too much about this. So I would recommend reading this if you want to know about the details of things, because it outlines what the operational differences between high-performance networks and Ethernet were at the time. And now Ultra Ethernet is converging those. This was 2022. Ultra Ethernet was founded slightly later. But that's something you can understand as a motivation. I don't have enough time to talk about all the details. But what is now this Ethernet ecosystem? What does that mean, the Ethernet ecosystem? It's a very abstract term. Just want to give you one number. I actually stole this number from another friend, Rambalaga at Broadcom. So he gives us this number at 2023 in OCP. 600 million ports, Ethernet ports, are shipped annually. Okay? So Ethernet itself is actually a high-performance deployment, because we deploy 20 ports per second. 20, 40, 60, 80, 100 ports deployed just while I'm speaking here. So think about this. This is completely crazy. That is the ecosystem that makes Ethernet. But now what we have to realize, that Ethernet is not Ethernet. Ethernet is a very, actually Ethernet is even used for the wireless network that we are using here. Ethernet frames on this wireless network. Basically everything is an Ethernet frame today. Like 99.99% of the traffic we cause as humans are Ethernet frames. But there are very different ones, like TCP/IP, which is what we're using right now to communicate. And there is RoCE, RDMA over Converged Ethernet, which in my view should really be called InfiniBand over Ethernet, because RoCE, for everybody who doesn't know it in detail, is really just take an InfiniBand header and duct tape it to an Ethernet header and then ship it over the wire, and with all its inefficiencies or efficiencies in case you want it. So it's really that. It's really InfiniBand over Ethernet. Okay, so let's double click on this a little bit. In some sense, you could argue, well, RDMA over Converged Ethernet is already a high-performance version of Ethernet. And yes, it was a high-performance version of Ethernet that was put together by heroic engineers based on great industry demand within 6 months. They had to have something. People said, well, we wanted, Microsoft being one of them, we want a high-performance interconnect, but we don't like InfiniBand, because it's too different from what we have. Our ecosystem is all Ethernet, so make it work. So what do? Well, you duct tape, or you put this InfiniBand header with all the goodies on top of an existing Ethernet header, and then you ship. It worked well, but it has some issues, especially at hyperscale. Right? It was designed in around 2014-ish. It was really a quick design, great. Again, I don't have enough time to go into all the details, what doesn't really work. I mean, there's a lot of buffering. The losslessness is an issue. We can talk about lossless versus lossy, because losslessness has a lot of problems, especially if you go long links. And so Ultra Ethernet has a different philosophy. And here already several industry people got together, if you can look at HPE, Broadcom, Google and Microsoft, discussing that we actually may want something else. Right? That was 2023, so history. And what happened then shortly after? Well, a subset of these companies founded the Ultra Ethernet Consortium. Right? So you can see these founding members here, we are one of them, but many, many other companies got together basically saying, we want something new. We need to fix this. We have 1,000x increase in this computation per bit transmitted. Great, that's a great baseline. And we have a lot of issues with the stuff we have today. But we want to use the Ethernet ecosystem and drive it forward into the great, shiny future. So what came out of it? Well, that was about a period of nearly 2 years. So Ultra Ethernet specification was released about 3 months ago. In fact, just 4 days ago, we released an update to this. This is not the latest anymore, so now we are at version 1.0.1. Fixing several typos, so it's not a great change. The big change will be 1.1 when we actually come out with new features, but I cannot talk about these new features here. This will be part of the session that we are doing afterwards. It's limited to Microsoft. Okay, then there is this paper that appeared 2 months later, basically making the spec a little bit more accessible to people. Yes?
So the missing one in this list is Mellanox and NVIDIA, right?
Yes. In the founding members.
Okay.
Today, NVIDIA is a full member of Ultra Ethernet, is contributing. They're on all calls. So yes. So these founding members. I mean, you can now argue with yourself why NVIDIA may not have been part of the founding members, but that was a smaller group. It was quickly extended. Actually, today we are more than 100 member companies. We'll get to this. It's a very, very large consortium. So the calls managing. Actually, we go here. So the ecosystem is very quickly growing. Thanks for the question. Perfect introduction for this slide. We have 10 steering companies now. So it's more. It's not founding companies, but steering companies. We have 17 general members and 51 contributor members. So that's about 100 companies. So we do have physical meetings. So we meet every now and then. This is a picture of the 24 meeting. So we had 60 members on site, but there's really 1,300 people signed up to the system and the mailing lists and everything. So I'm not on this picture because I'm the chair, so I'm standing in front and talking to people. This is Karen Schramm. She's my wonderful co-chair for the transport working group. So we are kind of the biggest massive change working group that we're working on. You see lots of people here, Mark Handley, Eric Spada, Torsten, and you probably see many, many familiar faces from the networking time. Okay. So this is the full list of companies now, in case you wanted to check. Again, many companies. It is a lot of fun having the weekly call with about 80 people online and trying to herd them together to come to a common goal. This is not always easy. Lots of interesting drama going on. Ask me over a beer. So that's actually a lot of fun. So now, what is this about from a technical perspective? So we are now comparing it to classic RDMA and what we've been doing in Ultra Ethernet, just from a very high level perspective, and then I'll double click into those going extremely technical in a couple of minutes. Classic RDMA really means RoCE, but also other RDMA interconnects for like InfiniBand or Cray Slingshot that were designed for HPC environments. Right? So they are typically lossless. Right? So if they're Ethernet-based, they're typically based on PFC, priority flow control, which is kind of violating a mechanism that was developed for something completely different into delivering lossless networking. It's not a great, it's kind of a hack, but it does work. CBFC is the more elegant version. You can actually save some buffer space, significant buffer space, if you use CBFC instead of PFC, but again, I'm not going into those details here. Ultra Ethernet set out to completely function over a lossy interconnect. Oh, I'm sorry, I should be careful. We decided to rename lossy to best effort because it sounds more positive. So I should probably update this. This comes from our official slides, interesting. And we also support lossless operation, but the base assumption is that we are a best effort network, which means the switch may drop messages or packets if the switch is overloaded at any time. There are several cool mechanisms how to deal with this, like packet trimming, for example, but that's the general assumption. Okay. Then classic RDMA is typically in-order transport and delivery, this go-back end mechanism. Like if I'm losing a packet, all the packets that are on the wire that come after that packet are discarded, and basically retransmit that from the beginning. So you lose a full BDP at every single packet loss, which is a total disaster if you operate in the lossy environment, because every packet that's lost loses all the BDP coming after it. BDP is bandwidth delay product. That's basically the capacity of the wire for a specific connection. So in Ultra Ethernet, we do out-of-order data delivery and out-of-order message delivery, actually. So out-of-order data delivery is how the data is committed into main memory, like how it arrives. That's fully out of order, but also the messages may be out of order. So there's now a communication going on with the higher level. Because in the good old RDMA, you just assume if I have a connection with somebody, then all this stuff arrives in order from that somebody. Right? Here, we have 4 different transport modes. ROD is reliable ordered datagram, which is basically in order. That's the same as ROCKY as we have today. It's just for backwards compatibility. We do not recommend using it because it's not very good for reasons I just explained. The real ones that Ultra Ethernet is using is RUD, reliable unordered datagram, or delivery. I'm sorry, not datagram is my InfiniBand term. I need to get my InfiniBand out of my head. Delivery. So reliable ordered delivery, reliable unordered delivery. There is a small extension to reliable unordered delivery in case it's an idempotent operation. You can optimize the network a little bit more, but that's a detail. Let's not talk about this. And then there's fully unordered delivery. Okay, so we have, in the old days, we have proprietary congestion control. So basically, everybody rolls their own congestion control. Azure Networking knows this very well. There's a long document internally how to do this. And this is not compatible with anybody. Like if I'm building my own data center, I'm running my congestion control and nobody else runs my congestion control. And so it's all different. UE is really standard configurable and flexible. And Abdul will talk a whole lot about this, how this works and how we've designed this. We have contributed quite some piece of that. In the old classic RDMA, single path routing, so no load balancing, we have problems with link polarization. If you have an ECMP issue, they could all go to the same link and then you're just messed up for simple reasons. In UE, we do per packet multipathing. That's very important. So actually every packet goes onto a different path. So it sounds like a total mess if you think about it, because you need to reorder and everything, all paths at different speed. But this is quite nice in the overall package. This actually works really, really well. And we have a per packet load balancing as well. So we can actually send 2 packets on the same path if that path happens to be twice as fast as the other path. Right? So it's not just oblivious spraying, it's very, very smart schemes. We have contributed a scheme that's called REPS, recycled entropy packet spraying here, and again, Abdul is going to shed a little bit more light on this. We have in the classic RDMA extremely large state per queue pair, so kilobytes of NIC memory, fast, expensive NIC memory per peer. Like today, NVIDIA's NIC memory is about a kilobyte or so, and you may know about thrashing, so you can actually, they have a little cache on their NIC, and then they run out of that cache, and then they move it into main memory, and if you have a bad access pattern, you thrash that cache. And then you move extremely slowly, like a factor of 10 to 100 slower than you should be. Ultra Ethernet is a fully connectionless API. So this actually, like, there's no connection. When I say connection, it's a misnomer. There's a context, there's a packet delivery context. Really nice, complete ephemeral zero-state RTT reliability state, and I'll talk about how that works in details in a couple of minutes. We have security that was added later. So the original ROCKY and the original HPC interconnects, they were not designed for security, because the model there was you lock your machine, you put a lock in front of it, and nobody gets in, and it's all fine. Well, the model we run at hyper data centers is a little bit different, because there may be a cable going through the street, for example, and then this must be encrypted. Or there actually, many companies provide services that whenever anything leaves the rack, it's encrypted. Even inside the rack may be encrypted. So this was added later, which is a bit of a problem because it was really shoehorned onto the existing framework and has a lot of issues. So it's n-square context. So if you have n nodes, you have n-square security context, one for every endpoint at every endpoint. My research group actually wrote 2 papers how to attack it. So there are pretty bad attacks on ROCKY. So you could have illegal memory accesses into any exposed memory if you share the same VM. This was quite funky. And in Ultra Ethernet, this is all built in from the beginning. Like, we have security discussions from day one. Eric Spada's driving this. I'm part of this. We do really cool stuff like cluster-wide rekeying, zero-state replay protection, and again, I'll talk a little bit about this in a couple of minutes. So this is the overview. This is the menu, what we're going to see in a couple of minutes. At the end, we are aiming at workloads that are MPI, OpenSHMEM, and CCLs. CCLs are collective communication libraries. In Ultra Ethernet, we call those star CCL because there are so many. And there's not just Nickel, like NVIDIA's CCL, but there's actually a Microsoft. There are multiple Microsoft CCLs, not just one. There are multiple A CCLs, one for AMD, another one for accelerated. There is about 40 different CCLs that you can look at. So this is why we just say star CCL, all kind of put them into the same bucket. Okay. So now what do we have? The application layer is basically aimed at primarily star CCLs, then MPI, and then OpenSHMEM. OpenSHMEM is gaining popularity with NVIDIA's NVSHMEM, pushing it out, and now we can have device-initiated communication, but that also all runs over Ultra Ethernet, no problem. We put those on top of an interface that's called libfabric. This is a pre-existing interface. It is not bound to InfiniBand. The other option would have been something that is bound to InfiniBand. There are many of those, like UCX, I think, and IB verbs. All of those were driven by Q pairs and not connectionless. We wanted an interface that does not give the abstraction of a connection to the user. Because the moment you give the abstraction of a connection to the user, there come all kinds of expectations with a connection. Like in TCP/IP, it's in order and all of these things. libfabric is fully connectionless. You literally just establish a universe of things, a universe of accelerators or whatever, and then you can read and write and whatever. You don't see any connections, right? That's the importance. At the very bottom, it's Ethernet. It's your standard run-of-the-mill, well, actually high-performance Ethernet. It's 100G lane speed or 200G lane speed. But these are the standard IEEE. We have a liaison with the IEEE at the PHY layer, where we basically look at what they're doing, sometimes scared. When you look at all this concatenated FEC, we're a little bit nervous. It's like, is this a good idea? Is this not? So we're trying to influence them for our and their good, but this is not specified within the Ultra Ethernet Consortium. So we have a liaison there. Then the data link layer is also partially in the IEEE. It's also IEEE 802.3. We have optional link level retry and credit-based extensions. So we actually use the good old IEEE headers. By the way, this is the Ethernet header that we've been using for 30 more years. Right? So it has a preamble, oh my God, and a start byte, destination MAC address, source MAC address, a type, and then comes the data, and then comes the frame check sequence. And the interframe gap, if you want to, you have to round to 8-byte, multiples of 8-byte, unfortunately. So this looks very inefficient, but there are ways that we can talk about later to make this much, much, much more efficient. It's not public yet. So there's credit-based flow control that we add at the data link layer in the 1.0 spec. Basically, you can turn off PFC. Like many vendors have this today. Actually, I don't want to name names, but many vendors you can buy this from today already. There is link level retry. So this is kind of an extension for PFC to enable optimizations. Or not extension, replacement really. It is not PFC, it's very different. And you can have link level retry, which is a mechanism where you can retry on the link, basically, not end to end, but to amp the reliability of the whole thing. Right? To amp the reliability of a single link in the environment. Then there comes the network layer, the IP layer, which has not been changed at all. That is, everything that's gray here is kind of already specified or specified in another body. Everything that's green is an Ultra Ethernet thing. Okay? So now the network layers, of course, sits in the data packet. We are using standard IP, so either IPv4 or IPv6. The good old headers, they look, again, humongous for an HPC person, like 20-byte header right there, plus optional things, or 40-byte header if you use IPv6. And then comes somewhere the UE payload. UE was designed at a time when we did not really consider latency super critical. Actually, it also turns out, packet efficiency super critical, because it turns out that at the speeds today, if you had a 100-byte header, that's a nanosecond. It doesn't matter. If you're running at a 200G per lane, header space is no issue anymore, so you don't need to optimize the headers to death. The only problem is if you send very, very small packets. Then you have an issue. So it's not a latency issue, a large header. It is a packet efficiency issue if you run at very small packets. Ultra Ethernet is designed for AI workloads that usually run relatively large packets. Okay, so we have that. And now let's go a little bit more into detail of the transport layer. I mentioned that I'm the co-chair of the transport working group, which is really the massive thing. Out of the 560 pages, it's 60% or so, maybe 70% is the transport layer. So here it gets a little bit more complicated. So IP, this is the transport, this is the internet protocol. So it's addressing, IP addresses. Then there is an optional UDP header, which you may be using. We got an IANA assigned port now, 4793. In case you're a port geek, that is the Rocky port ++++. So it's twice above it, because the next one was already taken by Huawei, so we couldn't get that. But it's twice better. So okay. So then we have an optional security layer. So there's an optional security header which has an ICV at the end, because it's of course security. So you can see the byte numbers here. That's the transport security sublayer. That enables OF1 key state per endpoint. We use key derivation function for rekeying, super cool stuff. And we have this full replay protection. That's actually super nice as well. Congestion management sublayer is really the window-based sender and optimized receiver congestion control that Abdul is going to talk about, including flexible load balancing. CC or CMS doesn't have separate headers because the CMS headers are in the PDS layer. The PDS is the packet delivery subsystem. That is kind of, you can see a whole layer structure, including nested layers. So we call these things in the transport here, by the way, these S's are subsystems or sublayers. These are layers, and then there are sublayers in here, okay? So the packet delivery sublayer really enables this zero RTT context build, request response control packets, flexible loss detection, all of those things that I'm going to talk about later. You see I'm going more and more into detail over time, but trying to make it in a way that you can follow easily. And then there is, on top of this, is the semantic layer, which really goes to libfabric. Right? That's the interface to the top. That has then the concept of addresses, send receive messages, deferrable send, RDMA or RMA reads and writes. So these are translated. This is messages. This is packets. We are then at the packet level. Here we are still at the packet level. This is security. And now down here we are at bytes. Right? So this is how the stack goes. It's a very standard stack. We just extended all these sublayers. Okay, wonderful. And then let's zoom in a little bit. Let's zoom into one very important aspect of Ultra Ethernet, which is really its load balancing philosophy. Its load balancing philosophy is very different from what everybody has been doing in HPC before, but it's very similar and compatible with what people have done in the data center, mega data center environments and good old Ethernet. So many of you are familiar with ECMP, equal cost multipathing. It was actually, in the good old days, it was designed for failover links. Right? So you wanted alternative paths in case something fails, you just go another path. But you can use that equal cost multipathing to enable multiple different paths potentially for every single packet. In each, multiple different packets go into multiple different paths. Because what it does is very simple. It uses it applies a hash function to the header of the packet. And you can configure which part of the header. And then the output of that hash function, so the input is the header, or parts of the header. The output is an index into a port group. So it's like an output port. So if you look at this switch, for example, here, so we have certain down ports. So this thing has 8 ports. It has 4 up ports and 4 down ports. Let's just focus on the up ports. So we are coming in with the packet here. Then the ECMP applies a hash function to the packet and selects one of those 4 ports based on the hash output volume. So if all packets have the same header, then they will go all the same port because the hash function is deterministic. Ignore failures. If you have failures, it goes different, but ignore failures. So now, but what I can do is I can introduce something that we call an entropy value. Somewhere in the packet header, the endpoint can decide to change a value or not change it. So now the endpoint knows whether 2 packets go on the same path or whether they are likely not going on the same path. If the entropy value is the same, we are guaranteed that these 2 packets are on the same path. If the entropy value is not the same, we have a high probability that the packets are not on the same path because they could still have a conflict. I mean, the hash function is having an n-to-m mapping, and m is much smaller than n, so obviously there is a conflict in the hash function. So let's look at this a little bit in more detail. And so this is all written here. So if we want to communicate from A to B in this network, we would use an EV equals A. Like, so it selects that path, and then it goes down. By the way, an EV, you can, in a fat tree network like this, or in a clause network like this, you can essentially imagining an EV address as one of those top switches. The way down is deterministic. There's only one path down. Okay? But we support different network types as well. So it's not the only topology supported. EV equals B goes a different path, so we hit a different top switch, but we also end at B. So you can see now how this works. The injecting NIC decides which path to take, based on all kinds of complicated measures that Abdul is going to talk about, but this is the general philosophy. Now, even if we are in the same group, going from C to D, we have a similar thing. So we have like going here, and we can go here. So this is the green EV and the red EV. So just for everybody to understand. So now, going back, where does this EV live now? Well, in good old data center, the EV was encoded in the UDP source port. because nobody needs the UDP source code port for anything. You can just like, as long as it arrives at the right destination port, nobody's going to check because the UDP is no context anyway. So you can update the UDP source port, or you can actually, there is a mode for Ultra Ethernet where we are not using UDP, okay? Where Ultra Ethernet directly sits on top of IP. We did not get an IP protocol number yet, but we are working on it. So we have a UDP number, and then you have a separate entropy field. The nice thing is, this will work over any switch you have today because it's at the exact same position as the UDP source port would sit. Right? So it's just all backwards compatible. It's Ethernet. You must make it all backwards compatible until the end of time. So this is a nice thing. Okay, so now we know how to do load balancing. Now I want to double click in each of those going into the transport layer in each of those areas, right? Going from the top to the bottom, the semantic sublayer. So the semantic sublayer is very important that it's compatible with existing applications that are written on top of libfabric. Now you can argue, well, there are not too many applications written on top of libfabric, and you're absolutely right. but those that are there are compatible. So you may actually implement a little shim layer that you can link to existing older IB verbs applications, for example, if you want to port them easily. But again, I can't talk about too much in that yet. So RDMA services, we have send receive, RMA, just standard stuff, mostly optimized for CCL semantics, scalable addressing to millions of endpoints, we'll see how that works. And then we have optimized extensions. So the one that I like most is deferrable sends. We'll see how that works. We use rendezvous, which has been done in HPC for ages. I mean, when I was a young student, I was working on rendezvous. And we have exact match as well to optimize the hardware in the NIC. I will not go into this too much. This is a very small thing, but super important actually for NIC architecture. Yes.
Just going back to the semantics
Yes.
layer, you mentioned messages, which is great. There's no concept of reliable stream like TCP, right?
No, it's all message based. You have a message itself is a little stream of packets,
Right.
but it has a concrete start and end. There's no infinite stream like in TCP IP where I'm just like reading and writing to sockets. Exactly. But you can, if you want, by the way, you can easily implement sockets on top of the thing because you could emulate it. It's very much like the sockets direct protocol in IFIP. A very, very good question. So let me first, and please keep asking questions if there is anything unclear. So let me first talk about the protocols. So it's really all optimized for specific use cases. Ultra Ethernet has 3 so-called profiles. So when I'm building a NIC, I may, as a vendor, say I'm supporting only the AI full profile, for example. I'm supporting only the HPC profile, or I'm supporting all of those. Like this is now a specialization opportunity for NIC vendors to cut down on the NIC silicon, to build smaller, more efficient, more optimized things for these 3 different use cases, AI base, AI full, and HPC. The main difference between those 3 is going to come in a minute, is the protocol they use for communication. And there's some bells and whistles on the side, and you can check the spec. Like some don't support certain atomics, others don't support certain atomics. Basically, HPC supports pretty much everything. AI full supports the subset that most people agree that is great for AI. And AI base, it's a very small mini version in case you want to make a really, really optimized AI NIC, minimal size. But it has some downsides because, of course, if you minimize things, you often lose something. So let's first talk about addressing. Addressing is very, very simple. You have an IP address, I mentioned. There.
AI-based targeting scale up or scale out?
So this whole Ultra Ethernet 1.0 is aimed at scale out.
Scale out only.
Correct, scale out only. However, you can use it in a scale up context if you want to, but it's just designed for scale out, right? So it's not optimized specifically for small distances, small domains. But we can talk about future plans in the closed session. Okay. So now if we address things, so we have here a standard address. We call IP addresses fabric address because we have a fabric. We also have fabric endpoints and so, but it's basically the same thing. Then there is a job ID that's new. So the job itself is part of the address, which is very important because it enables the scalable addressing to millions of endpoints and a fast lookup. Then we have a thing that's called PIT on fab, process ID on fabric endpoint. A fabric endpoint is something like a logical NIC. Imagine it like a logical NIC. Okay? And then we have a resource index, which you could imagine like a UDP port. That is now on the logic, on the process, on this logical NIC, we have a port. So you see lots of addressing because we want to address millions of endpoints. How does it go? We look at the fabric address. The network will route things with the fabric address to a particular NIC. right? So that's now standard stuff, so I don't want to talk about this. But then this NIC has a table of job IDs, like which jobs are running on that NIC. And these are parallel jobs that could be thousands of nodes comprising many, many NICs. Then we have this pit on fab business here, which you go from the job ID and then you find the particular process ID that is associated with that job. Right? What's very important is we can have many, many processes on the same node running with the same job. Right? I mean, it's pretty obvious, I hope. And then we have a resource index, which now you can say, well, there's an MPI service, there's a CCL service on that particular job. Right? This is how it works. This is these addressing components. Now you may wonder, what if I want to build a storage system? What if I want to build a system that doesn't have jobs? Right? I want to have a client-server system. Then we use what we call absolute addressing. So we have a fabric address, we have a job ID that is not used in that context, and we have still pit on fab and resource index. So we just address directly into the pit on fab, we address into the resource index, and that's how it goes. So now let me talk a little bit about the protocols that I was promising. So how am I now transporting messages over the network? Right? So first of all, we have a sender and a receiver, and I explained the standard HPC rendezvous protocol because that's probably what most people are most familiar with. So we have CPUs and NICs in these protocols. The job to be done comes from the CPU. So the CPU says, I want to send a message. This is a T-send, it's a tag send, but details doesn't matter. I want to send a message that has an address and a tag to the other side. And then in a messaging protocol, the receiver has to say, I want to receive the message into this address, and of course, I'm waiting for that tag. Right? So now there are two cases. There is a case that is called expected message case, when the receiver has posted that receive before the message arrives. Then there is a case where there's an unexpected message where the receiver has not posted that receive. So the problem is the receive tells you which address to go to. So if I'm sending you a gigabyte and you have an expected message, you just put it there. You know where to put it. If I'm sending you a gigabyte and you don't know where to put it, you can't do anything. I mean, imagine coming to your house with like a ton of rocks and you don't know where to put them. So basically what you say, you decline. You say, no, come back later. Basically, okay, this is what this protocol is about. Expected case, so how does it work in HPC typically? So this goes to the NIC. The NIC issues a rendezvous send message, which is a smallish message, usually of size BDP, and says, okay, I have something for you, but I'm not going to send you the whole thing, right? Because I'm careful. Then on the other side, the NIC will decide, well, you know, this is an expected case, so actually no, I just write this to the address. I've gotten that before. And then what it does then, of course, because the message may be bigger, it issues a RDMA read. So here is metadata in there that says, oh, by the way, I have more for you. And you find it at that address with that key. And then the receiver NIC issues an RDMA read of that message that completes here. And then it gets the response, and then it gets the whole, like, 2 tons of stones if it wants it. OK, that's the expect case. That's always great. And then, of course, it writes it to this address, and then it's done. Right? The unexpected case is a little bit more annoying. Like, you have this thing. Message comes over here, oh my God, no, I don't know what to do with it, right? So you may have very little buffering, so what you do then is this protocol sends a message back, oh, no match, I don't know what to do with it. Okay, and then comes the receive later, right? And then you can do the read. That's the rendezvous protocol in HPC. And then it does all of that, and then it completes everything, and everything is fine. Makes sense? That's the old protocol. Cool. Then we have an AI-based, so this requires hardware support for this whole.
Torsten, I have a quick.
Yes, please.
I was going to ask if there's a time limit there, otherwise you might denial of service.
Yeah, you can. Oh, this one is actually rather hard to denial of service. I mean, there's usually no time limit, but in the HPC, let me go a little bit broader. In the HPC context, you trust your user.
Yeah.
So you can probably run this against the wall if you want. Yes, if you just issue a whole lot of rendezvous requests and then the buffer is overrunning at the other side, and you may deadlock in that case, actually. Yes. I'm not sure you could introduce a time limit, but it's not prescribed. Yes.
Yeah, basically the same question.
Same question. Yeah, you trust that system. Okay. So then on the AI-based problem, but the problem with this is that people saw is that this runs underneath this protocol. So you need hardware to run this, to do this. People were concerned about this, that in AI-based, oh my God, I need too much hardware. And AI-based really should be the most trivial NIC you can imagine. So how does it work there? So there's the expected case. You would basically you have the same thing, right? You get this address. But what you do then, it's receiver driven. So you get the address from the receive side. You do a 1-packet send to the sender. The sender doesn't do anything. The sender waits in software until it sees the 1-packet send. and the one packet sent contains simply the address, and then you do an RMA write to the other side. A very simple protocol. It's strictly less powerful than this protocol, because in this protocol, I cannot have a receive operation that receives from anybody, because I have to know who I'm receiving from. Otherwise, I don't know where to send this message to. Right? So this only works for CCLs, while here in MPI has a specification that you can wait for messages from anybody, which you cannot do over here. But for AI, that's perfectly enough. Okay, so then the complete negative. How does the unexpected case work? Well, it's exactly the same, because now it's always expected, essentially. Right? Cool. But you already see the problem. Anybody sees the problem with that protocol? Yeah.
You have to wait on the center side.
Exactly. Exactly. You always have to wait. In the worst case, you gain an additional RTT, which can be really, really bad for small messages. Okay. This is why we came up with this deferrable send, actually a contribution from Microsoft, where we have a sender and a receiver, same thing. What we do is basically we have, again, the same thing, it's the expected message case, but instead of sending carefully only the start of the message, we just say, look, we just send the whole message. We pound the whole thing into the network, and then if that guy is ready, it'll just sync it. Okay, no problem. And it's called deferrable send for a reason, because if you do this, there may be, the NIC just says, oh, I can't take it anymore. But it says it fully in hardware. So this is kind of a weird, in my view, a weird protocol. Like it uses hardware support, but it doesn't really use the hardware support. This uses the hardware support fully. Basically makes it part of flow control. It just, the message comes and says, I don't know what to do with it. You just stop it. There are two tokens, an initiator restart token, a target restart token that you can identify these messages at the initiator and the target. And then later when the receive comes, you have a ready to resume, basically. This is a stop message, this is a ready to resume message, and then it goes like this. Has the big benefit that you don't have this back and forth here, you just sync it in the expected case. The nice thing about AI is that most of the time you're in this expected case, because you can schedule your workload pretty well most of the time, not always. In HPC, it's a little bit different. HPC are actually most of the time in the unexpected case, unfortunately, because it's not so good schedulable for the average application. Again, there are application difference. Okay, cool. So you're going high-level summary. This is standard in HPC. We know how to build it. There were lots of people very comfortable with this. Yes?
So for the deferrable send case, so the protocol needs to do a tracking at the packet level to resend the packet because it's out of order, right?
Yes.
Okay.
All of Ultra Ethernet is tracking at the packet level. We use very simple bitmaps for this typically. So you don't have to know anything about the packet besides whether it's here or not. So it's a single bit. If you look at it, it's not that much because packets are 4 kilobytes in size or 8 kilobytes depending on your MTU. And then you can track a whole lot of packets very, very cheaply. Like, that was not possible 30 years ago. That is possible now because we have this 1000x improvement. Yeah, but it's all per packet. Very good.
How many packets are you expect to track?
Sorry?
How many packets are you able to track at the maximum?
You can compute it basically. I mean, it depends on your NIC resources, but all you need is a BDP, essentially, if you think about it, because you cannot have that much more than your BDP times the out of order factor. And if you look at these networks, the out of order factor hopefully doesn't grow that much. So it's a small constant times the BDP that you need.
You have packet loss more than packet BDP, right?
Yes. Yes.
So you have other reasons to lose packets.
Yeah, exactly. But that depends on your implementation, how much you want to keep. That is not in the specification. So you got to.
So the spec doesn't say that the minimum how many do you need to track?
The spec says you need to at least a BDP times a small constant factor, and I think it's 1.5 or so. Yeah, the spec gives you a minimum, but a good vendor would probably use more. Probably have more tracking resources. Mm-hmm. Yeah.
And in the deferrable send, can the receiver buffer data before sending a response back saying it's up? I have space on my side. I buffer.
This is this M-length thing. So if the receiver actually has memory, it can store it locally, but it can also say, well, I didn't have any memory, and re-request the whole message. By the way, it's the same over here. This can also, you can discard that message here if you want it. You can reread the whole message if you want. So it's really flexible in terms of receiver resources investment. Okay, so that left side is very nice, experience in industry, but it has to send a fixed size packet here, right? A fixed size message, sorry. This is all AI optimized, so it can basically, this can react, this is better than the rendezvous protocol because it can react to a congestion window change while it's sending the first message. Here you have to decide, what am I sending this rendezvous send at, what size am I sending? And the congestion windows, sometimes they go up and down if you're a CC expert. So, and this is super simple logic because it doesn't require a read. Read is complicated to implement. And then this, the main argument here, it's simple to implement, but it requires software to get active. And it adds in one RTT in the worst case. So an RTT can be big. Right? So again, but it's super simple to implement, so it also has its place in some sense. So if you're buying a NIC, there are these 3 different versions of the NIC essentially. So packet delivery. So packet delivery, what we have here is a dynamic ephemeral context. So we have these services that I already talked about. We support all of the cool stuff, shared receive queue, out of order packets and everything. And selective acknowledgement as well. We just talked about packet tracking, so you can do a fully SAC, unless you run ROD. ROD forces you to do go back N. But everything else is full selective acknowledgement. Zero RTT startup, just to visualize it. In the good old TCP days, you do this, right? You build a connection and then you send your data. In UE, you basically just send your data. Right? So how does that work in detail? You may be wondering, oh, that's not so easy. It is not so easy. We have two connection state machines that I'm visualizing here. Actually, one connection state machine, but 2 different ways to visualize it. But the nice thing is, you can drop a state whenever it's convenient. There is no overhead whatsoever to reestablish a state. I mean, it's in the nanoseconds. There is a little bit of overhead because you need to allocate local resources on the NIC, but if this is in hardware, this is in the nanoseconds.
So this makes it trivial to migrate a process to another place.
Yeah, right. It's very nice, because you don't have any state, basically. Yes, exactly. You can just drop the state, migrate the process, and rebuild at the new position. You just need to make sure that you get the address translation right. I mean, that the new address is addressed. But you can also move the address with we know how to do this, like multi-homing and whatnot. Okay, that's all standard Ethernet stuff, multi-homing. We would just use that on top. Just to give you a little bit of a view of that zero RTT connection establishment machine, because it's quite cool. Here's again initiator target. So if you wanted to start, you always start at the initiator. I mean, it's obvious you start at the initiator because you know you want to send something. You allocate a local packet delivery context ID. PDC ID is packet delivery context ID. You send your message over. And now what you do, this is the state machine is building here at the initiator at the target, and this is a flow diagram. Now what you do is you have your PSN. Your PSN is you keep on a per peer, but you can reset that PSN if you want. It doesn't actually matter that much. It just has to be consistent within a single message. Right? So let's say we start at 4.5. We set the SYN flag of this packet, and now we say our source PDC ID is the one we just put here, but instead of the destination PDC ID, we put an offset, because we are putting multiple packets on the wire. Right? And then on the other side will not have the moment the first packet arrives, and it could be that the first packet that arrives is the second packet sent. Right? So if the second packet arrives, let's say, it'll see, okay, I have a source PDC ID 7, I have an offset of 1, and then I can look at the whole shebang in the packet, and I can compute where it needs to go, and I can build my PDC ID at the target, which I'm sending back in the ACK. But I'm sending all of those ACKs that have the SYN set, I'm sending all ACKs back with the with the source PDC ID 19 now. So now, the moment the first of those packet arrives, it doesn't matter which one, first of those packet arrives, I can go here into established because I got the PDC ID from the other side. And now I'm just moving forward. I'm also established the moment the first packet arrives back from the source. It carries both correct identifiers, so the offset is now the PDC ID. And I can move on, and then I move into established, and then like tearing it down is complicated, but tearing down is not the performance critical thing. Right? Tearing it down requires a round trip. It's always the initiator, I think, that says, I want to kill it. I want to send a close to the other side. I forgot it, maybe the destination as well, but it doesn't actually matter that much. Okay, so this is the full zero RTT startup protocol. It's actually quite cool. I think it's the first one in industry that I've seen that really does it consistently. So you can build connections at nanosecond granularity. Okay, cool. So then CMS, I'm not going to talk about this because that's Abdul's part. We have NS network signal-based congestion control and the receiver controls congestion control. And again, I defer.
I think Abdul has his hand up.
Oh, Abdul has his hand up. Yes.
No, sorry, just a quick time check reminder. That's all.
Yes. And so this all works together. Exactly. That's why I'm skipping this. There is a lot of academic stuff going on here in the context with a lot of collaborators here that Abdul is going to talk about that I'm skipping. And then the last piece I want to talk about is the transport security sublayer. It's really, really nice, but again, since we are on time check, I'll keep it very short. So we have end-to-end AES encryption. Key derivation, in case you don't know what key derivation is, talk to me about it. Absolutely awesome because it changes the key for every single packet, basically. It's super, super nice. We have very nice replay protection, which takes a while to explain. It's also written in the paper very cleanly. But How do you do replay protection, just for your brain? How do you do replay protection if you're not allowed to keep a per endpoint state? You don't know when it's replayed, right? Because you're not allowed to keep a per endpoint state because your PDC may vanish at any given moment. You'll find the answer in the paper. I can explain it later. This is a really cool idea. I'm very proud of this. And scalable security domains, and the whole thing is optional, by the way. It has additional headers. It has a little bit of overhead, of course. But it's all state-of-the-art, IPsec, PSP, everything that we know and love. We can have extreme scalability. So the improvement on IPsec and PSP is that we have group rekeying, secure shared domains with jobs, so O of one key state generally, like this scales until the end of time, and we have a very strong isolation. Cool, with that, I would like to come to the end, just overview. So we've talked about the motivation of Ultra Ethernet, how it came into place. It's a big ecosystem growing very quickly, and then I gave you a detailed overview of pretty much everything that I would find interesting. The most piece here is in the transport layer, and again, I'm one of the co-chairs, so if you have any questions, I can explain anything in excruciating detail if that wasn't excruciating enough yet. And then Abdul is going to talk about this is why I want to skip it. And if you want to find more information, you can read this paper. I think it's like 30 pages or so, but it's written for a scientific audience about the cool pieces in it. So yeah, thank you very much. And I'd like to give the stage to Abdul then to talk about congestion control, congestion management. Unless there are any quick questions. Okay, one last. So Abdul, you can set up while I'm...
Are the messages reassembled at the application, at the OS, at the NIC?
That's a great question. The message is reassembled into the buffer of, I mean, you have to have a receive buffer, right? That's the fundamental principle. And the message is assembled into that buffer directly, unless it's an unexpected message, but then you can also ignore it and just wait for the expectation. And it may completely arrive out of order into that buffer. And the NIC keeps a bitmap marking how many segments of this message are still outstanding, I'm still waiting for. And when the bitmap fills up to 1, you basically notify completion to the user. So this can, in terms of in order and out of order, it can be complete craziness in some sense, because they could fill up all at the same time, like with random offsets and random things. And then come these transport modes in. You can force the protocol to deliver these messages to you in order if you want. But most often you don't want to because you lose a lot of performance. Right? Then there is a really, really cool, let me just finish the last thought. It's a really cool mechanism how you can use matching to get in-order message matching. It's parts of the variable send. You can get in-order message notification, but fully out-of-order message delivery. So they will still notify you in order, but they can arrive in any order, and you can use matching, a little matching trick that I can explain offline. It's very, very simple. You just put the message ID in the match field. Cool. Yeah, thank you. And Abdul, the stage is yours.
Thank you, Torsten. All right, great. Thanks, everyone. I will be talking about the UET transport congestion control and load balancing, which I am a co-editor for as a section. For a brief time, actually, during the UEC inception, I served as a co-chair, and I continue serving as a steering member for UEC in the meanwhile. One more thing is the work is a combined effort with many people, many within Microsoft, and of course some we work with outside, and just cannot fit all the names here. So before going too deep, it would be a good idea to give a high-level definition or hand-wavy maybe explanation for these terms, just because it might be carrying different meanings. When you say load balancing, it's an overloaded term. So we are referring to it in the context of path or routing load balancing. Basically, if you look at the lower right of the slide, you'll see a toy topology, very simple, basic one. You have at the very bottom a few sets of servers. Each is connected to a top-of-rack switch, and these different top-of-rack switches are interconnected via the top-layer aggregation switches. Between Tor1 and Tor-n, to go between these two, you have 3 different routes in this example. And basically, load balancing is the mechanism by which you are attempting to spread your traffic as evenly as you can across the different viable routes. What you don't want is to hit the cap on one of them while the others are underutilized. It's too bad for your output. Congestion control on the other end, again, in a very hand-wavy manner, it is the mechanism by which you're adjusting or controlling the sending rates, cumulative sending rates of the perhaps several entities that are sharing one link in the network, or perhaps one receiver. What you don't want, again, is to overload any bottleneck where you're sending more than it can drain at a rate that it cannot absorb at, and consequently would end up filling buffers and causing massive queuing latency, especially for entities that are just driving by and contribute nothing to that congestion. This is, in essence, what Torsten was mentioning in his talk too, about the trade-off between latency and throughput. You don't want to run too hot on the links and cause massive queuing latency. Neither do you want to be too draconian and bring the throughput way too low just in order to be happy with your latency. And we choose here to talk about the two in conjunction, essentially because despite them being often, actually most of the time, studied independently, we do see a very tight interaction in certain cases, at least in the context we're working on. I will demonstrate to that in the next few slides to make sure it makes sense why we're addressing them together. So ECMP, Torsten again mentioned about that at the very high level. It is people exercise ECMP at the flow level. If you think of a flow or a connection, TCP connection, or even a Rocky Cooper as an entity that has constant source and destination port numbers and source and destination IP addresses, switches hash on these things, and they, based on the hashing output, decide on which of the viable forwarding options they would choose. In effect, it is equivalent to flipping a coin for a flow and saying you get one of the n viable routes to hash to. And it's great when it comes to ensuring normal packet delivery, makes it easy for detecting lost packet. But the challenge with these kind of things is the extent of hashing collisions you would see. That's, again, a toy example or simulation. We just wanted to demonstrate how bad the issue can be. In this case, we had 16 uplinks or ports, 17 through 32, and you have 32 flows that are all of the same size. So, and they're going from one tour to another. Basically, what you're seeing in that time series is on the y-axis the number of flows mapped to each of the ports in the network. Some of them are getting only one. I mean, typically 32 divided by 16 means if things are ideal and perfect, you'll get 2 flows on each port. But while it's random, you cannot really control it that well. So some of them are getting less than what they should, and some of them are getting 3x what they should in this example. And consequently, their completion time is in the 30-something milliseconds in this case, as opposed to a bit less than 10. So you have a 3x or more than 3x regression in performance just because you want to use that flow level hashing mechanism. Showing this bar chart because it will come up in the next slide again, you know, you're 32 compared to 10. And I'm actually going to show it here again, just to compare to something we call random packet spraying, RPS. RPS is similar to flow level ECMP in the sense that you also make it obliviously and randomly, but the main difference is you're not doing it anymore at the flow level. You're doing it at the much finer granularity of packet level. And therefore, instead of having only 32 choices to choose from across 16 ports, and yes, the margin of error is much larger, with the many, many more choices you're making for at the packet level, each can hash randomly or route randomly, you have, relatively speaking, much smaller gap throughput-wise, and that's why you are getting around 3x improvement. You're quite better, but you're still like around 25% worse than the ideal completion time in that case. Remember that 12.8 for RPS in red. I'm going to actually zoom in here from a congestion control perspective to complete that picture and again to tell you what I promised. That congestion control mechanism we were using, you see the labels on the x-axis, was called HPCC, High Precision Congestion Control, which is a great scheme in the literature, one of the very advanced ones actually. And it benefits from in-band switch telemetry. You get a lot more information about how many more bytes can you send to fill up your pipe bound delay product, basically, or your path bound delay product. But inherently in the design is the assumption that, well, you're going to use one path, therefore, and I'm going to optimize well for you that one path. Which is therefore, I mean, not to blame HPCC, it was never intended for multipathing. The ironic thing is DCQCN, which is an older generation solution, which doesn't have all the extra signals that HPCC has. Despite that, actually is working much better in that context when you are doing packet spraying or multipathing, and the reason is, if you zoom into the time series of the different flows that were traversing the network with HPCC, you'll see that their window size, which is a proxy for their sending rates, was too volatile, quite not very stable. Basically, one acknowledgement packet coming back to the sender might have indicated that on the path, the data packet that triggered me, there was so much X bytes available for you to jump and grab. The ACK right after, which was triggered by a data packet traversing a different path, might have indicated the very opposite, saying, well, you have to go down by Y bytes, and therefore you get that sort of confusion jumping up and down with the HPCC, which is not exactly what you see with DCQCN, despite the fact that maybe DCQCN was not initially designed or intended to work in that setting, but it ends up serving better that sort of environment. You do get more stability, hence, or consequently resulting in that better completion time, as we showed earlier. I'll show you later on the solution we have contributed, how it will help it get even better when we talk about it. Getting back to UET, the transport for UEC, and a few things here just to narrow down the context and clarify what we are going to be designing for. So UET was not really designed for any arbitrary topology, or at least we wanted to initially narrow down the space and focus on what perhaps much or most of the industry is focused on, fatted trees or folded claw network. That being said, our solution, as we have been exploring independently, few of us outside, can be easily extrapolated. We have actually some good experience and already some unpublished results with that, and where we show how we can make it work for things like a Firefly or a Click or any of your favorite direct connect topologies. But in that context, at least in the fat tree, all routes have the same length between a pair of servers, all meaningful routes you want to traverse, and therefore, your load balancing mechanism is not burdened with the extra effort of knowing the dimension. Like, should I use a short path on a non-short path? You will get away always working with a short path. To minimize latency as well, we chose to start by default at the full line rate, as opposed to taking a TCP approach where you start too slow and gradually ramp up with what is called slow start. We are not too concerned about bandwidth meltdown. We have some very good mechanisms to very rapidly actually adjust the rate and quite accurately. We'll talk about it, quick adapt. So that's why we were also comfortable to say, sure, let's actually start at the line rate and work our way backwards if needed. And finally, on the workloads, we are not too crazy about Incast, I should say, in what we have done so far in UEC. So as a starting point, we were focused on addressing the light extent of Incast 10-to-1. We did want to provide some cushion for adding more confidence and demonstrate that we can handle things like 100-to-1. But again, just like the first bullet, I'd like to say here what we have come to design, though it was not engineered for that, but actually does work quite well for much larger Incast degrees. And that's why we have suggested that this kind of work is more generally useful beyond just maybe an AI, ML, or HPC context, and can be extrapolated for storage or cloud computing more broadly, as we have also obtained some results to that end. So now I'll get to talk about what we contributed to congestion control. As Torsten mentioned, there are, by the way, this is the foundation for the for the default mechanism for congestion control, which is the networking-based one, there is an optional one, which is a receiver-based solution for better handling or for being optimized to handle incast. So I'll focus on the network-based one here. And in fact, elaborating on the name will give you a good idea what we're talking about anyway, before I go into more detail. So it's called SMART, and it stands for a sender-based, as opposed, as I mentioned, to a receiver-based solution that relies on ECN marking, hence the word marked. ECN marking, explicit congestion notification, that's a mechanism by which switches, when they have massive queue, or when they have queue built up, they will set a bit in the data header, and consequently the receiver will echo that big bit back to the sender to let it know that you have congestion. We use both actually, ECN marking, and as the last word in that name is saying, timed or delay-based or RTT-based measurements. Round-trip time inflation is also a good proxy for indicating congestion, and they're not exactly equivalent, I should say, ECN and RTT. In the literature, there's been a lot of debate and arguments. We chose to take an open-minded approach and actually to incorporate both, knowing that each has its own trade-off or downside, and we want to get the best of each. So we do utilize both signals, given that they're readily available anyway today. And we also, as I mentioned, have a component, a key one, that allows SMART to rapidly adapt its rate in both directions, actually, not just when you want to go down in incast, but also when you have a lot of abundant bandwidth, when a job finishes and you are in a position to ramp up quickly and grab remaining bandwidth. SMART does that very efficiently without significantly overshooting and causing massive issues. And the last word I'll mention or I'll comment about here is trimmed. We do actually, optionally, we don't need it, but we do utilize it when it is available. Packet trimming is an emerging switch feature, which is a great way for signaling packet loss, or actually identifying the lost packets more accurately, much more efficient in recovering lost packets as opposed to timeouts in general. We did, again, open-mindedly utilize it, despite it being initially proposed in a receiver-based incast control. We earned very similar rewards with it, and showed also how we can integrate it for adjusting your window and more than that. So here's a more qualitative description of SMART, or at least descriptive for what it is doing. In gray are the things that are not too different than what you might have seen in some of the schemes in the literature. So yes, we are a sending-based scheme. We are window-based as opposed to rate-based. And we are simple and very easy to deploy in hardware. But we, as I mentioned, worked better on providing the overlay of both ECN and delay signals. We did recycle some of the work that was done. I should be clear about that. But we're very happy how we orchestrated it together, whether things that were done in some work like Swift, or which is what Google does, or what we at Microsoft in DCUCN, or prior to that in DCTCP has done. We took a very good combination with all the lessons learned and put them in a very meaningful manner. As I mentioned in the few slides prior to that, when we were talking about the load balancing and how congestion control interplays with it, we showed HPCC and random and DCQCN, and demonstrated how the volatility of rate control was hurting the performance. With SMART from the get-go, we were very keen on making it actually react in a gradual manner. We don't want to be too crazy about jumping up or down and taking a big hit just because one of the many routes we're taking is congested. It's very true when you get to look at the mechanism and read about it. And in fact, one thing also to keep in mind is the analogy I always like to make about congestion control and load balancing is that when you're driving on a freeway and you're on one lane and there are many other lanes, your lane might have a few cars ahead of you, is a bit congested. You can either choose to slow down and stick to your lane, or change lanes, hopefully without making anyone get into an accident, or you can do a bit of both sometimes. So load balancing and congestion control are essentially trying to achieve these kind of tasks without having to be too confusing. What you don't want is to be like overreacting congestion control and masking away the congestion for load balancing, so it cannot anymore adapt for or when you have congestion, vice versa. So there's a very sort of nice game that goes in there, and you want to balance it well. And again, as I mentioned, we worked very well on being very responsive, especially on the way down when you have incast. But also, as I said, we do a quite good job on ramping up, and we gave more attention to fairness, essentially because some of the synchronized workloads in AI, some of them, not all of them, it matters if you avoid having extreme unfairness and essentially leaving few guys at the end of the story, like just hanging out lonely and having difficulty building up the rate or losing some time before they have recovered the entire bandwidth. So I'll get you more details now into the mechanism. We have a paper here you can look at, has a lot more details with a lot of evaluations. ECN and delay are the common stars for the entire show. But they're not the only ones. If you look at the truth table, essentially at the bottom, the rows are corresponding to whether or not you got an ECN mark. ECN, for those who might not be too deep in that space, is actually a little bit more responsive when you get congestion because you carry the congestion signal on the packet getting dequeued, even though that dequeued packet might not have been congested itself, but it helps you learn faster usually of congestion in the network. Delay signals, or round trip times, if you like to measure them as such, are more granular. They're multi-bit, and we use them as well here to check whether or not we're above a certain target that we'd like to achieve in our queuing latency. So basically, our choice is when you don't or when you do have congestion, whether or not your delay is excessive, we choose to slow down. But again, depending on how much or the fact if you're below or above the target threshold, we choose to go either gently or more aggressively on slowing down. Same goes for the case when you don't have ECN, we do increase. But depending on the status, as you would expect it, it would either be a gentle, fair increase, we called it, or something a bit more rapid called a proportional increase. The far right and left columns are corresponding to the cases when you do want to have rapid window adjustment, whether again going down, when you have a lot of ECN or when you have a massive inflation in your delay or packet trimming or any scary signal basically can be used to say, hey, I might want to check what I'm getting on the wire and sort of a reality check to avoid like having the delusion that my window is big and I should be sending a lot more. I'm going to go by what has been actually acknowledged. That's the ground truth. And the price you pay for a false positive is actually not bad. It should be supposedly close to what you're getting. We have a lot of work and results in the paper demonstrating how well that is designed. And vice versa, when you have very mild or really low, like no delay, no queuing delay, no ECN, it's a clear signal that, well, you know, you're not anymore flirting with that low queue occupancy. So it's time for you to go and grab more aggressively extra bandwidth. I mentioned a couple of slides ago that we are using the superset of ECN and round-trip mechanisms. In fact, we demonstrated very nicely in this evaluation. We were varying the number of flows, running many experiments of incast, and as you change them, there's a place where ECN usually does well, but a place where RTT afterwards with many flows can handle things a bit more gracefully. And we're showing the two versions, the pure ECN in orange and the pure RTT delay-based one in green. And then we're showing smart in blue, how it's actually getting nicely the minimum of the two functions, more or less, and sticking to the design really we wanted to, or the goal we wanted to achieve. That's a more elaborate tree-decision way of describing the mechanism. Did I get ECN? Well, I mean, was it ECN marked for the ACK or was it not? And then I'm checking the delay. Is it high? So the R being the delay here is bad, or is it not? And then I do like a gentle decrease, not an aggressive one, and so on. So we'll not go through the formulas and bore you to death here, but basically, mechanism is super easy, has been in fact already implemented in hardware. We demonstrated that, we evaluated it. It's actually very nicely also easy to do in a programmable NIC. I'm highlighting the two things again that also are very special for Smart, especially on the fast convergence and when we trigger quick adapt. Let me show you some more or some results to demonstrate now how well we're working. For this and for the next section, I'll be talking about load balancing. We're using a high-speed network in simulation, 800 gig. It's a 3-stage FAT tree, minimal round-trip time. We're less than 10 microseconds. We purposely chose the buffer size to be conservatively small, like only 1 BTP. We predict in the future we will be actually getting closer and closer to that sort of scenario. So we wanted to stress test that and demonstrate how well we can work there. We chose the target delay to be appropriately leading to half a queuing or half a BTP on top of the bare metal latency. And the ECNs, the Kmin and Kmax, when you start marking and when you reach the 100% marking, they are symmetrically chosen around that target RTT queuing-wise. We have a lot of experiments. I'm going to only show 2 here in the interest of time. Basically, that particular experiment or the 2 experiments we're showing here were permutations. We're varying the size of the flows. In one, we're running 2 megabytes. The other is a larger 32 megabyte. And you see here, like the CTF on the y-axis for the completion times. You see a light gray dashed line in each figure. This is actually the ideal, theoretical ideal line for what your performance would look like. If everything is perfect, you'll be aligned with that line. The closer to it, the better. And you see Smart in purple is actually doing the best in both. In the figure on the left, 2 megabytes, Rocky, which is using DCQCN, that's what, again, is now popular in many production networks, is actually doing not a bad job there compared to Smart. You see the regression happening more on the right, and vice versa. MPRDMA, which is a nice scheme in the literature, lightweight and so on, does actually well in the 32 megabyte, but not so much in the 2 megabyte. And then you have things like EQDS, the receiver-based scheme, which in this case, because the network is oversubscribed, cannot really reflect all the signals very accurately to the sender and do the rate control appropriately because, well, it is missing where the bottleneck is. And of course, Swift is what Google does. Again, we show in one case it is doing good, and in another case, not so great. Again, in some other cases, we've seen it to do twice as bad. But the point here is like, Smart is supposed to consistently, and we have seen it to consistently do well across all the cases, regardless of what scenario we looked at. So now, before I go into load balancing, again, I'd like to pave the way again for that discussion and remind you with what we looked at earlier. We showed in the past HPCC and DCQCN how the volatility in your condition control scheme was not so great for your performance and led to less or longer completion times. Here's actually what a simplified version of Smart looks like. I will not get into the details of that, but basically we did it in a short period of time. And you can see the wiggliness of the time series or of the window sizes. It is much better. And that's why you will see here your flow completion time actually will get better. Now, we are still what, like, 4 or 5% or a bit more of the ideal time. We're not saying, well, we should board the ocean to grab it. But in fact, we did start there thinking back then, as I'm paving the way for talking about the load balancing, we did start looking at like, okay, well, I mean, random packet spraying is pretty much like almost ideal, perfect for these cases. Everything is symmetric. All the routes have the same capacity. So just flipping the coin randomly for each flow is pretty good. Not exactly the best, but it should do quite well, and it is. In other cases, it might not be actually the best, and here's why we needed to come up with a better load balancing solution. Random packet spraying, it's not reactive. If all your routes are having the same capacity and all your players in the network, all your connections are using random packet spraying, it might be fine. But if one link has a degraded speed, or if you're thinking about it, like if some of the capacity on the second half of your journey is in the packet tree is degraded because some links fail, even if you can actually avoid black holes, if you can avoid these broken links, and or if things are still perfect, but some traffic is doing regular old-fashioned flow style, flow level ECMP, and you're trying to be the nice guy here and do packet level load balancing. Either one of these cases will clearly show you that, well, you're not going to get the best performance. Actually, you will have some major disadvantage. And that's why in such scenarios, you will need to have something a bit more adaptive. And this is what we wanted to do here. So when things are perfect, we actually do want to get something similar to random packet spraying, great performance. But when you have asymmetries in workload or in the topology or link failures and so on, you do want to get something much better. And we'll show how bad things can be with random packet spraying. All of that should happen while having a quite straightforward implementation in hardware. Which brings us to talking about recycled entropy packet spraying graphs. That's what we have contributed to also UEC. It's one of the two schemes that are optionally supported, and we'll actually compare to the other scheme here anyway. So just as we did with congestion control, I'd like to give you a high-level overview for what SREP's like. It's a sender-based, so the power is at the host. The switches and the network doesn't need to do really anything beyond what it already does today with hashing. In fact, I should say, though we have evaluated it basically with hashing for the convenience, just to bring it more easily to everyone's eyes in the community and say, look, you don't have to immediately migrate to source-based routing, but we know and we have seen it to work very well with source-based routing schemes. So it does rely on the same signal we mentioned earlier for congestion control, ECN. Again, the analogy I made about driving on the freeway, congestion can help you both decide what to, how much you should put on your brakes and whether or not you should jump off and go on a different lane. We do have some nice separation, by the way, between the two. Basically, at the high level, we defer the first task of removing congestion to load balancing. We say, look, don't freak out and try to be too tough on your window adjustment. Give it a chance. Let's see if load balancing will resolve the issue. And of course, it all happens organically without like any of these sort of complicated mechanisms. So organically, what will happen is initially you are being a bit gentle on congestion control. Load balancing should come and do its part. If it's not a load balancing issue because maybe it's an incast, well, congestion control will anyway kick in the right way it should. So both are very well orchestrated. We don't require any, in fact, there's a minimal state. It's more of a cache state only we retain or keep track of on the sender, which is not proportional to your bound delay product. It's not a function of your link speed. It's more a function of perhaps your burstiness or how much you're coalescing your traffic. That will be clear in a second once I give you the example on the mechanism. Basically, the secret is we're keeping the state on the wire, and we only momentarily cache it on the host for a very short period of time and then burn it right away as we put it on the next packet to depart. And therefore, that's a nice way for adding all that complexity on the host. I said that already, it does complement Smart and works very well in that case, but it also actually can work well across the board, even if you're not doing Smart. We've seen it work very well with DCTCP, DCQC, and a lot more schemes. So that's really a one-slide explanation and an example on the mechanism. It's a very basic one, but yet very powerful. So basically, as I said, the sender maintains a tiny cache of entropies. Entropies, as Torsten mentioned, are the proxies for the route that you're going to take when you're hashing based. And you don't really keep track of all the entropies or all what your acknowledgements are carrying. You only look at the good acts, the acts that are indicating there was no congestion, no ECN marking, If you're into the RT delay-based thing, I didn't have an inflation, no packet trimming, no nags. It's just a nice thing that indicates no problem. It's a good entropy that I would like to see again, hence the word recycle. I put it into my buffer, into my cache, and basically the next packet that will be leaving my NIC can recycle it. And if I have recycled everything that I recently added and I have no more, easy. I just flip the coin again and I move on to the next entropy I have not explored. So in other words, if you're unlucky and you got congestion again, we're going to flip the coin again. And there's that tendency or affinity for you always to recycle what is working. And for the times you're not very lucky, you will flip the coin perhaps a few times. Ultimately, you should have some sort of asymptotic convergence, as we have demonstrated in the paper. So here's an example to make it more clear. Let's say you are sending 10 packets, and apparently you have got no ACKs yet. You're just starting to do your transmission now. Nothing in the cache. So basically you do arbitrary choices, or you can make it like consecutive choices of entropy 1, 2, 3, all the way to 10. Basically, despite them being consecutive, keep in mind the hashing function of switches is doing a pseudo-random effect on them. So they will not really like go consecutive uplinks in a round-robin manner. It can be very different. But you chose these 10 entropies no matter what. And then in number 2, later on, you got the first ACK. And it happens to come for entropy 5, the fifth packet, actually. Because you sent them on different routes, they don't really have to be acknowledged in the same order that you sent. It's a green, nice packet, no ECN marking in this example. So great, I'm going to put it in my cache. But because I'm a window-based and I have more to send, well, great. The in-flight packets now are 9, and I'm allowed to send an extra packet right away. Fantastic. I'm going to send the 11th packet right away with the same entropy that has just came back fresh and nice to tell me, well, you know, that works. Why don't you try it again? Same happens again. The second ACK comes for 2. Nice packet, nice ACK. The 12th packet, therefore, is going to take it out from the cache right away. And again, state is being maintained on the wire, except for the moment between getting the ACK and sending a new data packet. That's when you need to cache it. Third packet, or ACK, in number 4, it comes back with entropy 9. Well, I don't care what the entropy is because it's ECN marked. I'm not going to do anything about it. I'm not going to save it. Later on, I happen again to be allowed to send a 13th packet. I look in the cache. I have nothing good anymore. Well, I move on to the next entropy to explore, which is number 11. That's basically it. And as you can see, it's very simple and very intuitive as well. I'll demonstrate here in the evaluation how well that actually works. A similar methodology to what we had. We're showing here also permutation, but I'll show you a lot more than permutation in the next slide. In the permutation case here, similar to what we looked at with smart and congestion control, the dotted or dashed gray line in the middle is the ideal one. You'll overlap with it if you're doing very well or perfect. Reps is the closest in that case, and next comes random packet spraying, the RPS one. That, as I said, you know, in an ideal case, things are symmetric, and well, it should be quite good. It will not be that far from the ideal performance. Then you see things like ECMP, which is, as I said, the flow level hashing one. We know it's not going to be great. And PLB, which is what Google does in their Falcon transport, happens to be something I've contributed. But it's a flow level one. We're doing much better at the packet level load balancing. Now, again, looking at the two tightest contesters here, reps and packet spraying, random packet spraying, orange and red. I want to show you the case where, well, you know, that shows kind of your true great potential if you do have actually link failures or if you have downgraded link speeds. In this case, we only downgraded the link speed for some of the links. And we wanted to see how well will reps do in that case. Very interestingly, it sort of self-adjusts on the routes that have lower capacity without any direct kind of explicit, you know, signaling from the switches about like, oh, you have to go twice less likely on that path than the other path, or whatever. It's gonna dynamically adjust and pretty much send the same utilization, or if you want, it's gonna match the capacity the weight, if you want, is matched by the capacity of each link, remaining capacity, and therefore it gets you the best throughput close to the ideal dashed line above. Random packet spraying in orange, which though does very well when things are symmetric. In this case, it's going to again flip the coin evenly on all the routes, including those that are running at lower speed. And as such, they will hit the ceiling, they will start getting tremendous congestion, and they will continue not learning the lesson and saying, well, I want to choose the different routes uniformly, and hence they pay that kind of price cost-wise. One thing I wanted to zoom in, even in the symmetric case, remember here the red and the orange are very tight when things are symmetric. Well, actually, we were interested, like, why does it make a difference here? Like there's around 10% or 7% improvement with reps compared to random packet spraying. And we show here the time series of the queues, how they were evolving over time. And you have two bands, like a right and the left y-axis. The right one is showing the queue size, left one is showing the draining rate of the ports. And you can see in the lower figure with reps, queues are very nicely stable. They are not underutilized, they're not hitting zero, so they're all running at line rate. And that's evidence from the output. Whereas with random packet spraying or oblivious packet spraying, you can see these kind of wild fluctuations in the queue sizes, and every single color you see here has at some point hit zero, which means the link was underutilized, which is evident again from the throughput plots on the top. That's again the microscopic behavior sometimes is easier to explain, helps you understand what's going on, even though in general, on average, well, I'm sending the same number of packets on every port, but every mistake I make on a short time scale actually adds up and will cost me the performance. As I said, we have a lot more evaluations. This is a very dense slide, and I will not go over every single thing here, but starting from the far left, we tried different incast experiments, different permutation ones, different tornado ones. They're micro benchmarks, and we're showing many of these schemes, including MPTCP, one of the classical works in that area, nice piece of work. Adaptive Rocky, what NVIDIA, what some switches do today, adaptive kind of load balancing in the switches. You see, of course, reps, PLB, the Google one, MPRDMA, something again nice and lightweight. Bitmap is actually what I mentioned has been contributed to the UEC as another optional feature, the one in the inverted triangle in blue. Flowlet is some nice work from Ali Dad's group in MIT, and Oblivious Packet Spraying, and of course ECMP. Basically, you might see in one of these figures, like, oh, well, there is a tight contender somewhere. But if you check one of the other figures, you will surely find that, oh, well, somewhere else it doesn't do very well. And that's the beauty of reps. It's actually dominating the performance throughout all the scenarios we have tried by a good margin, actually. There's no scheme that will not have, let me put it that way, more than 30% regression compared to reps. If you look in at least one of the experiments, you will find something like that somewhere, even if it does well in some other cases. As I'm going to wrap up actually in this slide or the one after, let me bring this to closure with a nice add-on we did for reps. And basically, given the very nature of reps, with the tendency to recycle things that are working, then comes the very nice point of link failures. How does it work when a link fails and it's black holing and your routing engine or SDN or whatever it is has not cleaned it up? You still have that entry saying, oh, well, for that destination, I'm allowed to send on that port, even though it's a disaster to send on it. Well, the good thing is, of course, reps is not entirely amenable when at the onset of that link failure to completely avoid it or to avoid taking a dip into the black hole. But the nice thing is once it's taken a dip in it, it will not really go again and recycle it for the very simple fact that it's not getting anything back to recycle. So it will cleanly keep on using these that are still functional and working. So that's on the first order of business. Now, the second thing we realized here is like, okay, great. Since we're recycling and we're taking chances when we are having nothing in the cache to recycle, when we have any kind of worry that there's a bad thing out, like we're losing packets, like a timeout or some sort of things like that are happening, we actually fall back to a conservative recycling scheme that when you're not finding anything in the cache, you might be better still sticking onto something that is working, even if congested, as opposed to flipping the coin and taking yet another dip into the black hole. That's what we call freezing. You stop being aggressive on exploration. We show here in the bottom how reps, when one link fails in a time series here, how it takes a little dip and then it gets back up and doesn't really keep on taking a dip. In contrast, oblique spec spraying above, you see like a main degradation because the problem is with things, anything that is oblivious like random packet spraying, it's not just gonna like get some packets stuck in the wire and then that's it. It will keep on adding more and more and more, and your window is only bound to that much. So you're getting more and more of your throughput getting stuck somewhere and never unlocked. And that's why you see like the degradation, despite the failure being, relatively speaking, not that much, but you lose 3x or 3/4 essentially of your performance, and it takes you a long time to get back up, consequently resulting in more than around 40 to 50% regression in your completion time compared to reps. So that's my last slide. We have demonstrated again for the UEC context how reps does very well. And as I said, it can work very well also for full-face routing. It's not carved in stone to be working only for hashing base. We have implemented in hardware, and in fact, continue seeing the great gains that we have seen in simulations. And again, because of how malleable reps is, and the fact that it doesn't really assume everything should be doing reps for this to succeed, you can go with very partial implementations and start seeing gains for both the traffic that is doing reps and for the traffic that is not doing reps driving by. It will still benefit from the lower queues and congestion that reps will pave the way for. With that, I'd like to thank you for listening. And I know we don't have maybe much time, but I'm happy to take any questions in the few remaining minutes.
All right. Thank you.
Any questions?
Yes, let's take questions.
Do you want the mic? Okay.
I think
Okay.
we've got you in the room.
So was any testing done with non-packet spray flows traveling through the network at the same time? Like legacy flows?
Yes. We do have that. I should actually put a pointer to a paper with a lot more evaluations, and we did exactly that. We varied the fraction of traffic that is not doing graphs but doing ECMP, and we showed that the rest being graphs and remaining being ECMP, how they interact and how both that are doing ECMP, flow level ECMP, and how those that are doing graphs are both benefiting.
Thank you.
Thank you, Aaron.
Other questions in the room or online?
That's really nice work. I was curious about where congestion usually happens and why. Is it on the receiver? Is it on the network? And a quick comparison to the receiver-based congestion control to sender-based that you showed.
Yeah, so it is highly dependent, on the workload. And if your question is like, in our network where we see it, I've seen. Well, I think I'll defer that particular part to people who are, more hands-on on our network. But I've seen it in some other operator that I'm not going to say the name, and in much of the literature, to be really very frequently happening on the edges, like the sending or the receiving TORs. And essentially, again, if you look at it from both perspectives, this is where the first tier of oversubscription is hitting you. The front line of drops will happen there. Vice versa on the last hop, the receiving TOR, that's where like things can gang in together and cause some incast at the receiver. Our workload in some places, definitely with storage, does actually, essentially lead to incast. It's no secret. And the other reason is, your entropy as far as like the number of flows competing for bandwidth at the edges is not as high or as great, if you want to look at the information theoretically, as in the core, where you have a lot more flows crossing the core of the network, and you know, the cross traffic, the extent of packets being interleaved, the hashing function having much more diverse input, all of these things make it a little bit better usually in the core once you have overcome all of these kind of tiers one after the other of being oversubscribed.
I'm curious, the HPC community has looked at a lot of sophisticated adaptive routing protocols that involve a lot of state on the switch and communication between switches. And I'm curious how this sort of simple approach compares with those. Is that something you guys have looked at?
Yeah, we have. So I think that, so in this particular work, we demonstrated this, I think hexagon blue adaptive Rocky. That is actually a switch-based adaptive routing, where think of it like, in a way, you're trying to send on the shortest queue when, among the different routes you are having. So you try to load balance as such. And I don't remember if we did also a look ahead, one step forward again, because usually what's well understood in the literature is if you only base your routing on your local information, actually it might be a disaster. And many pieces have demonstrated that. So people are now starting to say, oh, let me have a look ahead where I don't just get the status of my next hop on the forwarding port being good, but I'm going to get some signal from my neighbor next doors to tell me, like, if I send to you, am I going to be in good hands or you have some problem? So that way I can reduce the extent of issues. But even if you have that one step look forward, it's still going to have, in general, the same challenge that, well, when you are choosing your path, you'd better make an end-to-end choice because, as you know, as an example, in the fat trees, you go up till the root or the top of that fat tree, and then on the way back, you have only one path on the way back. So you might do a greater job getting up, climbing, but then if you have a broken link on that one path coming back later on, it's too bad. You cannot really deal with this. Or if you have a congested one because of some local traffic having congestion, again, that forward path looking thing might not do anything for you.
Yeah, just to add to this, that was exactly the main point that Abdul pointed out. I mean, these schemes turn out to be pretty brittle in the failure case, and in mega data center providers, you have a different tolerance for the network going down than in HPC.
Right.
So this is much more reliable.
Any other questions online? All right, let's thank our speakers again.